Hi everyone, I'm Max. One of the things I work on is preparing and test solving problems for Google CodeJam. I'm going to describe the problem triangles from the CodeJam 2022 World Finals. When writing most CodeJam problems, we come up with an interesting programming problem and then invent a fun story around the problem itself. This time, we didn't write a story and just stuck with a geometry problem because geometry is fun enough as it is. So here it is. The program must read from its input a set of points in 2 dimensions. Then, the program needs to figure out a way to join up as many of those points as possible into triangles while satisfying certain rules. The triangles cannot cross each other. Any 2 triangles must be either outside of each other or one must be wholly inside the other, except that the vertices of a triangle can touch the edge of another triangle. For example, these configurations are okay, but these are not. The input set of points could be very large, so a program would be too slow if it tried every possible way to divide up the points into sets of 3 to make triangles. So we need another method which can solve this quickly even for a large number of points. If you want to try this problem on your own, head to g.co/codejam after the round ends, where you can read all of our previous competition problems and submit solutions to get feedback from our judging system. And make sure to stay tuned, because once the round ends, someone from the CodeJam team will walk through the solution on the live stream. Good luck to everyone competing.
Hi everybody, I'm Pablo. I'm an engineer in the CodeJam team, and I wrote the triangles problem, and I'm going to talk through some details about its solution. So in this problem, we have a bunch of points that we want to join into triangles. And we want those triangles to fulfill some definition given in the statement. So in order to solve the problem, what I'm going to do is I'm going to constructively prove a theorem. That's important. And then that construction, then we're going to make it efficient enough so that our algorithm can actually perform it in time. So here's the theorem. The idea is that in a set of 3 t points, we can make exactly t triangles, so basically use up every point, if at most 2t of them are collinear. So the direction from top to bottom is kind of immediate, because if we have more than 2t collinear points, by the Pigeon principle, at least 3 of them are going to end up in the same triangle and then not make a valid triangle. My direction in the other side is not. So let's look at it. So first, let's start with the case where there's the set of collinear points not really saturated. It's kind of far from the maximum. So let's say there's at most 2t minus 2 collinear points. So in this case, our strategy is going to be find any triangle that doesn't interfere with anything else, because since these points are all collinear, we cannot grab more than 2 of them for a valid triangle. So any triangle is going to be okay, because it's going to keep the number of collinear points small enough. So the way to do this is, let's say we have lots of points, right? We're going to find 2 extreme points. There's multiple ways of doing this. One is the convex hull, but the easiest way is just to sort by x and then by y, and take the 2 most extreme points. So in this case, this would be these 2 points, right? So we pick these 2 points, and now we want to find ourselves a third point, and we're going to keep the triangle we pick in a different plane than everything else. So that way we ensure it doesn't interfere with anything that happens later. So because these are the 2 extreme points in this order, we know that there's not going to be anything on this side of the line. There could be some things on the line, but that doesn't really matter too much. So the way to do this is like we rotate from here like this, and we find the first point by angle, right? Because we already know that there's nothing on this side, so as we move like this, there's going to be nothing, nothing, nothing until the first point, right? So we're guaranteed that above this line, there's going to be nothing there. So we could try this triangle. Of course, this in particular doesn't work because there could be a point here. But in this case, we can try from the other side. So we rotate this, and then we find this point. And then this triangle will work because this line also has nothing towards this side. The reason the second one worked is because all the points, and the first one didn't, is because all the points are below the line that joins our first 2 chosen points. So we need the direction. We don't need to check which is the right direction. Ideally, we can just like go towards both sides and just keep the one that works. If both of them work, that's fine. We pick either one. Okay, in this way, we get rid of one triangle. We maintain the hypothesis, so we just have a smaller set to solve. Now for the other case. So let's say we have at least 2t plus minus 1 collinears, right? So in this case, if it's 2t collinears, we want like every triangle is going to have 2 points from the collinear set and 1 point from something else. If it's 2t minus 1, there's going to be 2 points from the collinear set and 1 point from the other points in all but the last triangle, or all but one triangle. Okay, so let's do that. So let's say we have this big set of collinear points, right? We have 3, 6, 9 here. Let's say 10. And then we have 5 other points. So let's say 3 here and 2 here, right? So this is exactly 2t. So what we're going to do is going to split the 2 sides of the line. And since we have 3, 6, we want to pair them with 6 collinear points, and we're going to pick like the top 6. So 1, 2, 3, 4, 5, 6. So we're going to pair this up and then pair this up. And then again, because these 2 planes are separated by a line, triangles here and triangles here are not going to interfere with each other, so we can just solve that separately. If there's 2t minus 1, one of these is going to have 1 fewer point. So now let's see how to solve one of these where all points are on one side of the line. So we can do something very similar as we did in the first stage. If you have all the points on one line, and some more points all here, because we pick the first 2 points in the collinear set, so the highest 2 in this case, and because we know there's nothing here, we can start rotating our imaginary line until we find the first point, and then we're guaranteed there's nothing above. So this triangle here is in this plane, everything else in this plane, so this triangle doesn't interfere with any other triangle. And we can keep doing that. So we do that, we remove this, then we pick these 2, we rotate again, let's say we find this triangle. Notice that if there's many points that are tied by angle, we want to pick the closest one, right? Because we can like slightly skew the line so that there's still a separation line between the 2 planes. Okay, so we can be going until we have very few points. So let's say we get to 4 points, which is going to be the case if we have exactly 2t to start with. So if we have 4, then we have 2 others here, it's going to be fine because we are going to just find this triangle and this triangle. It's going to be okay. However, if we had only 3, we can run into a problem because that means we also have 3 points not on the line. And if we just find any triangle using 2 from the line, it's possible that the other 3 end up being collinear. So for this particular case in which we end up with 3, we need to do something else. Since we only have 6 points, we can brute force it. Just try a repulsing combination and see what works. It's not hard to convince oneself by cases, which I'm not going to do now, that every case with 6 points in which not more than 3 of them are collinear is possible to build into 2 triangles. The hardest one is when you have 3 sets of 3 collinear points like this. And we can solve this case with like one big triangle and another smaller triangle inside. The other cases are somewhat similar. And this solves the problem and proves the theorem. However, we also need to implement this somewhat efficiently. Taking triangles out in the first phase or in the phase where we're processing the collinears takes linear times, which is quadratic overall, which is okay. But the first phase can be slow if we keep recomputing the largest collinear set, because as we take triangles in a greedy way, the largest collinear set might change. So there's a couple of ways of dealing with that. One is to compute all the collinear sets at the same time and keep them updated in a sort of priority queue, but that can be very slow, even though complexity-wise seems efficient. Another way is to only recompute the largest collinear set when we know it might have changed, which only means recomputing in logarithmic number of times. But again, both of these approaches add some logarithmic factors and some large constants and are going to be too slow. So the easiest way to deal with it is to just ignore the largest collinear set at the beginning and keep doing the greedy step in which we just find triangles. So we find one triangle, then we find another triangle, then we find another triangle. And at some point, if we can't do it, so if we try both directions and neither works, that means that every remaining point is collinear. So at this point, we can just undo some of the latest triangles that we built until this is a saturated case, and we go straight to phase 2. So with this improvement, which is also simpler than the others I mentioned to implement, it's a little bit more clever, you can do quadratic time overall, and it's very fast. And the implementation is not that tricky. So that's it for the solution. Thank you for watching.